Good afternoon, everyone. Thank you all for coming. My name is Mike Edgar, and today I'm going to be talking about laser, which is static analysis for Ruby in Ruby. So a little bit about me. Just told you my name. The website is carbana.ca. I am not Canadian, I just like the name. And laser, which is what I'm going to be talking about today, was my undergraduate thesis at Dartmouth College, and nowadays I just started as a Google engineer. So, what is laser? Laser is a attempt at building real static analysis linting for Ruby, and it has two goals, which are actually quite distinct, which is to find errors in your code or potential errors, and just general style issues. A key part of that is that because Ruby has such a complex grammar, you need a pretty advanced tool to find style issues. So, what's static analysis really about? Static analysis at its core is finding properties of a program, any kind of non-trivial properties, without running it. This has a lot of uses. Biggest one, the most important one today has been optimization. Static analysis is why all of our mainstream programming languages have gotten so fast. It's very useful for error discovery. This is where it's really becoming, where it's been more explored these days. The Clang team has an awesome static analyzer for C and C++ code. And just for general statistical analysis, finding out things about large corpuses of code in a given language. And static analysis is, for the most part, quite hard. These are a few of the problems that we might try to solve using static analysis. Finding loops, finding what constants are in a program, doing type inference, which has been some focus in Ruby, but not too much. Exceptions. You see this in Java, actually. It's part of the spec. You need to do exception inference. Dead code elimination, period inference. These are all examples of static analysis. And for the most part, they're all undecidable without any aid to the compiler, which means that we are doomed to fail in terms of actually doing a perfect job of all these things. Now, a lot of you are probably wondering, why are we talking about static analysis in Ruby? It's an incredibly dynamic language. Anything can change at runtime. And, of course, we have no types anywhere, so how do we even know anything? But, as I said, we already aren't going to figure everything out. All these problems are already undecidable. So the real question, and the question that I've been focusing on for the last year, is what can we do reliably? What can we figure out? And the answer is actually quite a lot. My first motivating example, the one that I first came up with about a year ago when I decided to start this project, was I wanted to write a tool that, given a Ruby method or a Ruby program, find out for a given method whether it requires a block when you call it, whether it will use one optionally, whether it will ignore one completely. And when I actually formalized this, I found another group of methods that actually make no sense, which I call block foolish ones. Those are the ones that will try to yield if you don't give it a block and will not call the block if you give it one. Those are in error. So just to make it clear what I mean, here's a block required method. It doesn't always call the block, but you cannot call it safely, as in you cannot call it without generating an exception unless you provide a block. A block ignored method, just something that adds, something that adds two numbers, something that definitely does not use a block no matter what. Block optional, we know and love these. These are especially common in our file operations. They're all over the standard library. All of them enumerable in 1.9. They're all block optional. And this is just a quick example. And this is a block foolish one, which is just the inverse. And this seems incredibly foolish, but that's why I call it that. But you'll notice the only difference is that we screwed up the order of the guard on a block optional method. So these are all very hard problems. Checking if a method, determining if a method is block required is equivalent to the halting problem, and all the other ones are even harder. But the truth, they are. But the truth is, before I go any further, Microsoft's done a lot of great work on the halting problem. And they're all highly tractable. And I knew this from the start, because when we as Ruby programmers look at our methods, we all know instantly which category these methods fall into. We can tell. It doesn't take a lot of difficult work. And that's because we use Ruby syntax, we use very common idioms, and it's just very simple to actually figure these things out for most cases. Now, because these are undecidable and unrecognizable, you can always write a method that it can't figure out. And that's okay, because how are we going to do this? Yeah. No one actually writes yield if the halting problem is true for a given thing. That just, you don't write that code. If you do, then laser's not the tool for you. And I'm sorry. But the truth is, real code is tractable for a lot of these problems. And that's why we write these tools. That's why we're interested. So when I started, I found that two major challenges face Ruby when it comes to this. The first thing is metaprogramming. Metaprogramming is what makes Ruby so fun to use, in my opinion. It's what makes it fascinating. It lets you write incredible code, but it also makes it very hard for a tool to look at a bit of code and see what it's doing. For example, a lot of active support and whatnot uses string class eval just to create methods, alias method chain, for example. I don't know if the current implementation uses string eval or define method, but either way it could work, and a tool needs to be prepared for both of these. If you aren't, then you're not going to know what methods are there, and you're already, as soon as you see a call to one of those methods, you're going to have no idea what's going on. So that is something that you have to solve. And then the other thing is that we need flow analysis. And this is something that hasn't really been done in a strong general way for Ruby yet. Most of our tools just look at the abstract syntax tree. You can do flow analysis on a syntax tree. It's just a lot more cumbersome and a lot less fun. And as we saw in the block usages example, you need flow analysis. You need to be able to tell which branch is taken in a given context. If you can't, then you're done from the beginning. So for metaprogramming, I struggled with this for quite a bit. I tried to find a way that didn't involve just running the code, but the truth is that's pretty much what you got to do. And you may ask, is that still static analysis? Well, it is static analysis unless as long as your program does something other than create classes and methods. As soon as you hit I/O, then as soon as you hit I/O, then all of a sudden, we're not going to keep running the code. We're going to switch to more traditional techniques. But, and I have a note on the slide here, is this enough? I'm not sure. I'm not sure if this is actually enough for for example, Laser, I'm going to say right now, it doesn't work on Rails. It's probably going to be a while before it does. And so I don't know if this approach yet is going to work just right for that. But the truth is, when you think about your programs, how many methods do you add to your program after a given point in time? I call that point in time the actual load time of your program. Up until then, you're still constructing classes through actual runtime code. You're still adding methods. But after a certain point of time, you aren't creating new methods. Method missing and the idiom of creating a method dynamically on that is an interesting challenge, one I haven't focused on yet. I don't think that's actually too tough of a technical problem. But in real-world code, we don't add lots of methods and classes at runtime. And this is, again, for applications. Testing frameworks, those are going to do some interesting things. But I'm focusing primarily on applications. For the first prong of Laser's approach is just run all the code you see in the program until you hit I/O. And while you do that, capture all the global state changes. And it does that using a pretty interesting technique we'll see in a sec. And then there's flow analysis. You can do static analysis that is flow insensitive. When I started doing research on this, there actually was an implementation of the type inference algorithm I use, which we'll talk about in a sec, which was flow insensitive. And that had some limitations. Ruby's -w is, for the most part, flow insensitive. And that is part of the reason why some people have expressed frustration with it, is that it is limited in that sense. And flow sensitivity, for the most part, makes pretty much all analyses better. It's just an extra signal in when you are trying to figure something out. So flow analysis really is Laser's major contribution to Ruby and to the literature on this so far. And we do that by trying to build a control flow graph for Ruby code. We then put it in what's called static single assignment form, which all the compiler buffs in the room will know about. I did consider continuation passing style, but I had no idea what that would look like with Ruby. So I went with static single assignment form. And after we build these graphs, we just do all the analyses on these graphs. Not everything Laser does is on the graph. Some of it is done before that, really trivial stuff like seeing if you shadow a variable with a block. But the interesting stuff happens on the graphs. So what's a control flow graph? It's just a representation of a program. It's a graph of things called basic blocks. A basic block is a sequence of instructions which, when run, always starts at the beginning and always terminates with the last instruction. You can't jump into the middle of a basic block and you can't leave early. This is a simple control flow graph For some abstract language, whatever. And as you can see, it starts on B1, goes into B2. This is just a simple loop, and at the end it exits. You can't leave after the assignment to comparison, and that's just a fundamental part of basic blocks. These are fundamental to how most optimizing compilers work. What instructions do we use? Now, this is something that takes a lot of thought. The Rubinius people will tell you they put a lot of work into deciding what bytecode they use. Well, we put a lot of work into, I put a lot of thought into picking the instruction set to use for laser. And your choices there are going to frame all of your analyses and how much work you have to do to support those analyses. Laser's instruction set is extremely simple, and sometimes that's a bit annoying, but here's what it is. In those basic blocks, which is what we end up turning every single Ruby program into, is just these basic blocks pointing to each other, you can assign a local variable, you can call a method with dynamic dispatch, call super, raise, return, jump, or branch. And while I don't support all of the Ruby language so far, I've managed to pigeonhole everything into just those instructions. Don't do throw yet. That's one of the limitations that I'll be talking about later. But yes, catch and throw is something I'm still trying to figure out. But I do suspect it'll end up turning into a raise-like situation. So first question is probably, well, there's a whole lot of features that don't seem to make sense in that context. Most obvious one is instance variables. Well, I turn those into calls to instance variable and set while ignoring overrides. And there's two reasons for that. One, I didn't want to add another instruction, just because I didn't want to have to do more work later. Two, it forced me to also simultaneously solve the problem of instance variable set with a constant string. And for example, calls to that are very commonly generated through metaprogramming, and sometimes they're just used to break encapsulation. So I wanted to be able to solve that, and I figured by just doing this for the short term, it would force me to actually solve that problem. I do the same thing for class variables as well. Keywords like alias or def or class, those are all method calls. Class turns into a lot of method calls and branches and whatnot. Blocks create a constant proc value and stick it in a temporary variable. And this doesn't really always work. There are some things that there aren't actually existing method calls for in Ruby. So I use a special class called Laser Magic. C Ruby folks will know the frozen VM object. That's pretty much my frozen VM. So for example, when you set or get a global variable, it turns into a method call to Laser Magic. And I mean, maybe someday I'll change this. For now, it's actually worked out. So, real difficulties. Ruby control flow is complex and unpredictable. Exceptions come from pretty much every method call. At least until we do further analysis and figure out what things can raise what methods. So when we first build this control flow graph, every method call is going to possibly raise an exception. And also, currently it does not model all control flows yet, which is a big problem. And this just results in very ugly graphs. So here is the graph. You can sort of see what's going on there for that simple while loop. I've got it hooked up to GraphViz to automatically spit these out in PNG, which is pretty cool. But yeah, and all those little red ones that are solid, those are possible exceptions. The dotted ones are ones it has determined to not exist. And this is just two nested classes. So luckily, I'm the only one who has to look at these while I'm debugging Laser. You don't have to worry about it. But the size of them is a problem for speed and efficiency. All right, so static single assignment is a special form of a CFG. In this, every variable is assigned only once. Local variables and the compiler made temporaries. This requires rewriting the control flow graph, renaming variables. In Ruby, it involves changing the structures a little bit in the situation of unassigned variables. You also need to add a new instruction type, but you don't need to know about that. You just don't. So yeah, the key point is that it distinguishes variables with the same name that are assigned on different code paths. For every variable, it also simultaneously calculates where it's used with respect to flow, which gives us the flow sensitivity, which makes this powerful. And in Ruby, while I'm doing this, it just so happens that's the perfect time to, pretty much the only time, when you easily figure out when a local variable can be assigned conditionally on one path. So that's how I actually surface that information. All right, so now we're ready to start analyzing stuff. But first, we need to talk a little bit about how Laser represents the Ruby object model. I pretty much re-implemented the whole thing in Laser. There's a Laser object, a class module, proc method. There's big overlap here with Rubinius, and where I think there could be a lot of good work, either me stealing everything they did or vice versa. We'll see how that works out. But an example of this is Laser method. There's one instance of these for every method in the analyzed program. It implements the basic method functionality, and it also has methods on the method for answering analytical questions. Yield type. All you do is you type whatever method.yield type, hit enter, and it'll tell you, is it a block optional, foolish, whatever. Return type for types, for example. And what's interesting is, because of this, we can subclass Laser method if we want to add more information. Now, by default, a Laser method just uses the built-in techniques that I'm going to illustrate to figure out the answers to these questions. But if you want, and I do this for the send method in particular, and allocate, I actually subclass Laser method and say this is actually a send method, and this is really what happens when you call it. That should only be necessary for special things that are really low level in Ruby, but we'll see. All right, so let's get some answers. The first stumbling block is dynamic dispatch with dynamic types. And yeah, so I decided everything's going to be a method call in Ruby. Now I actually have to own up to that and figure out how to handle all these different method calls. So I use what's called the Cartesian product algorithm. This was the first paper on this, I think, was in 91 or 92 for Smalltalk and Self, a guy named Atchison. Hope I'm saying that right. And the real question is, how do I know what foo's type is here in the case of bar.run XYZ? Obviously, that depends on bar's type. We all know that. But it also depends on X, Y, and Z's type. And by type, I mean the concrete class here. I don't have any more advanced type system in Laser besides that. So here's a quick, simple example here. We want to find out what the bottommost X's type is in this horrible little line of code. And you can see here, it does depend on both the receiver of Go and the argument. If it goes to the double class, it'll return an integer. If it goes to the string class, it'll return a string. Or if you put a string into double.go, it'll get but that doesn't happen. I lied. So yeah. And the answer is to try all of the types, the Cartesian product of all the argument types. So that means every possible combination of bar's class, X's class, Y's class, all need to be tried, and then you union the result of these all together. Now, if one of these raises, its type is empty, so that actually handles sort of handles that case silently, and you just end up with all the possible actual return types. This is really nice because, for one, it's conservative. It is actually going to get every possible type. It may get some extras that aren't in the real program, but it will get all of the correct ones. It only requires one pass through the program. An important part of this is that, well, if we go back to this example, every time we discover a new type for X, we have to go and recalculate the new parts of the Cartesian product. That's how you get the one pass part of it. It does require a finite number of types. This is not, I tried to add tuple types to the language, to Laser, and I was able to add some tuple types to it, but some instances resulted in infinite types, which kind of ruins everything. All right, so Laser's implementation. For every single one of these combinations of the Cartesian product, it just duplicates the entire control flow graph. The SSA, the fact that it's SSA means that we're flow sensitive. And this may be one of the first times someone's combined a flow-sensitive Cartesian product algorithm, come up with one. I don't really know. But yeah, so you end up with this very nice way of expressing the question, Laser method, what is your return type for types? What it does is it just goes and says, well, what's the control flow graph for those types? Give me that's return type. And then it checks it against expectations and returns it. Now, some interesting stuff happens in the control flow graph, but the questions that we ask our classes and our methods, they all go through the control flow graphs, which lets us isolate all these things to relatively simple, old algorithms. I don't use any algorithms in this that are not at least 20 years old. Static single assignment comes from the late 80s out of IBM. Control flow graphs go back to like the 50s or 60s. So yeah, if all of our analyses use CFGs, and we need to parameterize the CFGs by the argument types, and all of our analyses can be parameterized by the argument types. For example, if we want to ask if something yields, we can actually check if that depends on, say, the type of some argument. That's a bad example. That probably doesn't actually happen too much. But yeah, that actually gives us more accuracy whenever we want to do an analysis. It just makes it a lot slower. Only 2 analyses aren't currently parameterized by that right now, and that's yield type, because that doesn't really make any sense. And I forget the other. All right, so let's find some bugs. I already showed you some error discovery, actually. Back here when I said check return type against the expectations, well, all that does is it goes and says, all right, what is the expectation of, what do I expect this method to return? Now, you may be thinking, well, that doesn't make any sense. Well, in my opinion, it does, because if something's named 2s, I expect it to return a string or a subclass of that. If it's 2re, I expect an array or a subclass of that. And if it's bang, you really better return a Boolean. And so these are, and so right here we just see it checks against that and adds an error, if, a warning level error. It isn't a fatal error, but yeah, there's about 10 different levels of precedence of errors in Laser. And so yeah, it just tells you, hey, that may be a mistake that you did there. And it took 16 lines of code to add this feature to Laser, and that's not much of an anomaly. The hard part is building the control flow graph. It is built in pretty much one file, which is over 2,500 lines long, and I really got to work on that. But that's really the hard part. After that, you're writing algorithms to work with the general data structure with very simple instructions. So the analyses end up quite compact. Another one is unused methods. This one took 2 days to add reliably. And the insight was just we're already calculating dispatch. Every time we see a method call, we're using this Cartesian product algorithm to say, okay, what methods could this call? What are the receiver types? And how about we just mark, while we're doing that, why don't we just mark every method we see? That's pretty cheap compared to the cost of doing all this other stuff. And at the end of the run of Laser, we'll just see what isn't used. And this pretty much, you can see right here, that involved adding that one line, method.benUsed. I have it highlighted, it's kind of hard to see. And then this to the runner of like the actual entry point to Laser. At the very end, it just says, all unused methods. Unused methods iterates over every class and module, and then over every method, checks if it's had that been used flag set on it, and then returns it. And then it creates a warning. And because we already model send and public sends dispatch, we already account for that. It comes out to around 15 to 20 lines of code just to add this one feature. Unused variables. Now, there's some easy cases that are variables that are assigned but never read. And Ruby already does this. It's in the parser, which is a little, a bit of, it's a place to do it. No. Anyway, but it can't handle even trivially dead code. If you write if true or if, something that only returns a string, it can't really, it can't tell which branches aren't taken. And also it can't handle variables that are only used to compute then unused variables. So for Laser's approach, we just go through every variable in the control flow graph, find all the transitive uses, and something's considered unused if it's not returned, if none of its transitive uses are returned or used in an impure method call. So if you add a bunch of numbers together, and I can prove that they're numbers, but you never return any of those numbers, then all of them are considered unused. This also transparently works for method arguments because those are just local variables as far as the control flow graph is concerned. By lowering the representation so far, a lot of things just fall into place. Multiple assignments, for example, those are just desugared into single assignments and branches and whatnot. So yeah, this turns into a dead simple work list algorithm. And it's O of V, which is the number of variables in the SSA control flow graph. It's usually linear with the code size. I haven't checked this with my implementation, but for the most part, in other languages, it's shown to be typically linear. And yeah, this entire algorithm was just 55 lines of code on top of what was already there. And we get flow sensitivity, and dead code does not affect how it sees this. And so here's just a quick example. I cheated and just ripped this from the Ruby, the R specs for Laser. But yeah, you see this here, and it calculates a constant, which is just some number in like base 5, and checks it, and Laser here figures out one of those branches because it has some basic purity analysis. It can tell that turning a number into a string is a pure operation, And it trims off the lines at 7, 8, and 10. I'm sorry, it prunes the else branch. So it knows those lines are dead, and you see that the second and third spec check that. It also sees that the variable d on line 4, it calculates it. It even assigns it to a variable j later, but then j does nothing. So it manages to kill all those. Very cool. I should probably add something so it checks if x is unused, because it isn't, but I don't have a spec for that. All right, so block usage. This was the whole motivating. This is what I really started out to do, and obviously it's going to be harder than what I've already showed you. Unused variables are cool, but I really didn't have a thesis if I could find unused variables in Ruby. I mean, I did. I just would like a better one. So why do we care? Well, for one, we can find errors. If you give a block to a method that's never going to use it, so you probably are a bit confused about what you think that method's going to do. It's not going to kill you. It's not going to raise an exception, but you probably messed up. That's a silent error that Laser can find. The other case is when you don't provide a method that very well could use it. You may not even notice the first time, because like that silly rand example I gave before, it may not raise the first time you do it. It may be that only after you've deployed your application, you hit the edge case where it needs a block. So that's a big thing. Finding errors is a big thing, and that's what Laser's focused on. And block foolish methods, you already screwed that up. Another idea is that we could auto-generate documentation. If I get really good at this, then maybe I could hook this up to YARD and have it automatically spit out whether it yields or not. That'd be pretty cool. And maybe someday we can help the compiler writers in the audience that work so tirelessly to help us all out. So, as Ruby programmers, how do we tell if a method needs its block during its execution? When we look at a method, how do we tell that? Well, if it calls yield, either not in a block given type conditional, and without catching a local jump error or one of its super types. Yeah, that's when I first discussed this idea. Someone said, "Oh, what about catching local jump error?" Well, I had to account for that. You do. Yeah, exactly. Yeah, I mean, there's things that it can't do. That's proven. But the other thing, you could introduce the explicit, ampersand block variable in the method signature and then call it. You could use proc : new to get a hold of it. You could then, or you could not even call it right there, but you could delegate it to a method that does call it. And as long as none of these are guarded by block given, define yield, any user define. Oh, yes. You mean like alias method and the alias keyword?
Square brackets versus call. Make sure.
Oh, yeah, absolutely. And user-defined aliases to those methods. But yeah, or you can define an alias to block given. And there's also, did anyone here know that iterator ? is an alias to block given? Yeah, that's also one. I did not know that, but it is. So. Or someone could grab a hold of one of those and do is that not nil. So there's a whole lot of cases that you could do to construct one of these, and they all exist even in the Ruby core standard library, though I don't think some of those do, but the main ones do. So we need constant propagation, and we have constant propagation. We have the ability to prune those branches, as I showed you earlier during the the unused variable case. So what we do is there's a little bit of support in the control flow graph builder to make this easier to analyze. But for the most part, we just copy the unparameterized CFG twice. There's no reason, there are reasons to parameterize this, but it's for the most part, it's not worth it, and it would save a lot of memory and time. On one, we assume there's no block. We pass a fake-in block argument to the constant propagation system. And on the other, we tell it there is a block. We tell it always return true for block given and all those things, pass in a dummy laser proc, and then we track the aliases looking for attempted calls. By aliases here, I mean aliases through the method. So if you capture proc.new into x and then set y to x, or call a method with it, it's a very conservative analysis, but it tries to make sure it can see if you've possibly called that block. If we see delegation, if you call a method with that as the block, we recursively analyze at that point. We then ask that method, hey, I passed you my block. Are you going to use it? Because I need to know. And this whole thing was 79 lines of code. There's 19 lines of a conservative alias analysis. I mentioned it here because I don't use it for anything else yet. And it handles almost any real Ruby code you throw at it. Again, there's always cases that it won't be able to handle, including real-world cases, I'm sure. But this was this is Turing unrecognizable. That's harder than the halting problem. Ruby's not as hard to analyze as we've been led to believe. And a big part of this is the syntax and the idioms. For example, block given, everyone uses block given. That's just one example. Yield, by being an actual keyword, makes it a lot easier for the control flow graph builder to create separate code paths for that to make it easier for later analyses. Woo. Now simulation, we talked about this at the start. I said that we are just going to run all the top-level code. CFGs are representations of a program. They're clearly executable. So when Laser sees top-level code, it runs it. And it gives up after it runs for either a long time, either because you wrote an infinite loop while you're defining classes, or just that you wrote really long code and Laser doesn't want to waste your time. Or when it hits I/O. Okay, I'm turning you off. When it gives up, it switches to all the analyses that I've already told you, even for the top-level code. So this is literally interpreting Ruby in Ruby. And you're probably thinking that must be really, really, really slow. But you're wrong, because it's way slower. I've got a bug actually in the GitHub repository for someone who just wrote a top-level loop to 100,000, and it ran for 20 minutes, and they just gave up. And that is a problem. I'll talk about it in a sec. But yeah, it's really slow. Luckily, it only uses it again. Defining classes does not take that long. That graph looked big, but it's actually not that many instructions. And this gives us some benefits. While we're doing this, it tracks which edges of the CFG are actually taken. Whenever something's simulated, and during constant propagation, it checks to see what things are clearly never run. This makes analysis later faster, and it could possibly optimize startup time someday. There's something called the theory of partial evaluation, which you may want to look up. It's way too heady to talk about now, but it's all about this idea of partially running a program and figuring out what things we can ahead of time ignore. And a large part of the overhead of loading 300 classes into a Ruby program, there's tons of checks in there that can be completely elided. So that's another possible path for this. There's not enough time to keep talking about different analyses. There's some other cool things. I hit most of the good stuff. But it's time to talk for a bit about the challenges that Laser faces. The biggest challenge is that there's a bust factor of 1, and I have a job now, and I don't write Ruby. So it's maybe a little less than 1. And there's also a bit of technical debt that makes this a bit harder for other people to jump in. I'm proud that I got an academic project actually the source out there. That doesn't usually happen. But that said, there's good corners and there's bad corners. I mentioned the control flow graph builder. That's 2,500 lines, and it actually needs to grow. That whole thing needs to be modularized and made better. And some of the internal APIs, I showed you some code snippets before, and I'm not terribly proud of how they look because they could actually be cleaned up quite a bit to be more clear. The arguments could be better. And that also makes it harder for people to jump in. It's hard to analyze a control flow graph when there's so many different things that you can do with it, and it isn't really clear. Also, Laser understands Ruby. It does not know C. I've been developing it using actually 1.9.3, and that's mainly because I've fixed about a dozen Ripper bugs that are actually now going to be in 1.9.3, making it good enough to actually, yeah. Laser does use Ripper. It's good enough to actually, power a sort of Ruby implementation. I think it's finally good enough that it can actually power a Ruby implementation. And so right now it only works with Ruby 1.9.3. My continuous build server just can't actually run Laser yet until I get 1.9.3 on it. But yeah, the thing is, lots of MRI is in C. Laser does awesome when it sees just Ruby calls, but eventually you're going to get to C calls if you're using YARD or MRI. And the current solution is to have stubs for all of these, and not all because I don't have that much time, but for lots of these methods with annotations. And yeah, this is just a few lines from string.rb in the Laser repository. And there's a couple thousand lines of those, and that's just not going to work. And the obvious solution is to use Rubinius's libraries. And I really, really like this, and I think this is really where it's got to go. I haven't done it yet. They need a little bit of extra support to analyze well, because Rubinius does use, well, a lot of the type checks that happen in normal C Ruby, they expose in real Ruby, and those are going to need some extra help from Laser to understand as accurately as it needs to analyze these appropriately. There's no technical barriers to this, though. It really is, a week or two of work, and I could drop in 95% of Rubinius's libraries and drastically improve both the state. Get rid of all these, and these aren't even completely correct. Yes.
University of Maryland is doing a static Ruby analyzer.
Diamondback Ruby. I believe they're using OCaml, but yeah. I'll talk about.
They have a database of those annotations that you might be able to use.
Yeah, well, I did. The thing is, that was for static. That's a very good idea. I didn't even think of that. Talk to me after. I like that. All right, but yeah. So there's also some good news, which is that a lot of the things that Laser could do. For example, it already finds guaranteed races in your methods. For example, if you try to call a method that doesn't exist, and it can actually prove that. Incorrect array, type errors, stuff like that. And I figured I'd put only one meme in this entire thing, but it doesn't tell you. And some of that is, for one, like some method calls are supposed to always raise. If you call the method raise, I'm not going to yell at you for always raising in that method because you called raise. Or you may write a wrapper function that does some formatting for a string and then calls raise. Well, I shouldn't yell at you for calling that. I haven't figured out exactly what that heuristic is supposed to be. And it's not going to be just as good as did you call raise. Arity errors should be reported. I don't actually think that would be that much work. I just haven't gotten around to it. But that is something that does work. The other thing is Laser's pretty slow. We'll never get Rubyists to value static analysis if it's slow. The compiler writers aren't going to like it if they have to add, if none of their users want to use the static analysis that can make things faster because it turns their build to a couple hours. It's a lot like testing. People don't run their tests if they take half an hour to run. Laser isn't that bad. I haven't tested. I haven't had it. It isn't good enough to test on enormous code bases yet, but I suspect it is too slow. And a good amount of the low-hanging fruit has been picked. All the algorithms used are at most O of n squared. There's only one that's O of n squared, and that one can't really be made too much better. So it's not. They aren't really algorithmic problems. I'm using algorithms that much smarter people came up with 20 years ago. So there are a few things. The CFG encoding, well, because I use so few instructions, that could be made a lot more compact. That could improve things a lot. It would also mean analyses could be made smarter and avoid doing extra work. I say Laser is Ruby in Ruby. There are two parts of it right now that are not in Ruby. One is Ripper, and that may actually change soon. I've been working on a new parsing thing, but we'll see. And the other is that I replaced the basic block class. I talked about basic blocks earlier. That got rewritten in C++ because it just made things so much faster. There's still fallback in Ruby, but yeah. The other thing is that a lot of this can be cached on disk. The whole standard library, for example, say I drop in all of Rubinius's libraries, well, all of that stuff can be analyzed once and just saved on disk. The main problem right now is I use too many hashes with default procs, and those can't be serialized. So, yeah. So everything I've talked about so far, they aren't really technical issues. The main thing right now is that the control flow graph is not conservative. Now, conservative, we hear that mostly about MRI's garbage collector, and being conservative is a bad thing there. Rubinius has the precise garbage collector. Well, that's because garbage collection is not undecidable, and building an accurate control flow, a precise control flow graph is, unless you have a very bad language, a non-Turing complete one. So yeah, there's three categories of solutions: precise ones, which is Rubinius's garbage collector, and there's conservative things like the typical optimizing compiler CFG and the YARD GC, and then there's wrong things, which is what we have. And it's true. There's no wiggle room. There are things that Laser will be just wrong about, and that sucks. And the main problem is, and what it comes down to is that not every possible control flow through a Ruby program is represented by edges in the graph. The easy solution is to add an edge from every block to every basic block, but that makes it useless and slower. So We're not going to go with that. And the real solution is just to actually figure out just how to actually model these problems as minimally as possible. Currently addresses catch and throw. This was brought up earlier. Right now, Laser does model exceptions. I'm pretty sure I don't do retry, but I haven't done that yet. But it does do all the other stuff with exceptions really well. It even handles weird cases like next and through loops and all that stuff, and ensure. But catch and throw adds another level to the equation because any method can also catch or throw. And I don't know if that's going to be too hard or not. But fibers and continuations, not too worried about that just yet, but those are control flow constructs that have to be considered. Proc cases, bindings make things horrible because you could pass just call a method with a block, and that method could change a local variable. Well, a control flow graph needs to be able to see when its local variables change or things are going to get messed up. That may not be solvable. We'll see. Luckily, most people don't do such a horrible thing. And a big part of Laser is that I need you guys to not do the worst things in the world. None of the compiler writers are happy because they are laughing because they have to support the worst things in the world. When you call a method with a block, they have to be ready for the fact that you're going to change all the local variables in that scope. And that inhibits enormous optimizations that could be made. This control flow graph isn't conservative yet. That's not the worst thing in the world because I'm not a compiler. I'm not going to generate the wrong program for you. We want static. I want static analysis to succeed. That's the more spurious warnings you get, or the lack of warnings that could be given. That depends on accuracy. That needs to be improved. The other thing is the compiler writers do want these analyses. I'll put words in their mouth and say that a lot of these things, and the things I've talked about mostly so far, they're not that big a deal for compiler writers, but there's a lot more that could be done. Escape analyses, alias analyses, and we all want those things to be made that much faster. So yeah, Laser's had a lot of successes. It's the first foray into deep static analysis for Ruby. It does a lot more than I've even talked about today. I didn't even talk about the style stuff. It can do some pretty cool style things, and it'll rewrite your code to fix them too. And I'm working on a new parsing library that exposes the full parse tree, including white spaces, comments, all that stuff, so that it can be even better at that, and so that it can know exact column numbers and give Clang-style error reporting. That's another big thing. It models exception frequency and type inference. Could be a little bit better at that with respect to rescue clauses, but it does successfully model that. It can see when you have arity errors, all that stuff too. Does constant propagation and branch pruning. It may not help programs today, but that's okay. So Laser's a year old, but extremely young. I truly believe it is vital to Ruby's growth. I think this is a huge opportunity, and I think this is really what Ruby needs in many ways to help stay relevant in a world where people are starting to look for other tools. I think that this can really make Ruby much more attractive to have this sort of support. In a year or two, I could see Laser actually supporting Rails. It would need an extra plugin. Not going to lie on that one, but it could absolutely do that. How much time we got? My phone. Oh yeah, I turned off my phone because people kept tweeting me. 2:54. How much time is that? Oh, some guy tweeted while he was here. That's okay. Thanks. All right, so here's just a quick thing here. Let's take a look at temp.rb. We've got two classes here, and this shows off just a couple of features, not too many, but yeah. So, I don't know if people are laughing at the horrible code or the people tweeting, but yeah. So yeah, this is something that I wanted to find an easy way to. I could have used an if or something, but this. It uses gets.2i to pick something out of there. And so RECV is going to be either a foo, a bar, hello, or nil, because you could return 10 or something like that. And then it calls do stuff with 3. So if it goes to foo, it'll return 3 values. If it goes to bar, return 3 values. We know it's not going to return 2 because we're good Ruby programmers, and we know that 3 is an integer. So there's nothing wrong with this code. So let's run And most of this time it actually is taking right now, in my defense, is it loading the standard library and analyzing it, because, as I said, I'm not caching that yet. But it should only take about 5 more seconds, 10 seconds. Oh, there we go. Okay, so there are a couple things. There's a blank line at the end. There's a little bit of dead code. I showed you, you saw the dead code. String can be wrapped in double, my bad. I didn't even do that on purpose. So now let's make this, let's remove one. And now we'll make an extra one. So yeah, now we're updating our bar API to return 4 things, and the line below that's consuming that API has not been updated. It isn't prepared to have a 4th value, and it's only unpacking that tuple into 3 things. So let's see if Laser, how's it doing?
When you say fixable, do you mean automated fixes?
Yes. The style thing, I mean, it only even tries to fix style things. But yeah, there we go. See that second to last line there? RHS value being discarded. That's it seeing that we have the potential here to have 4 things on the right-hand side and only unpacking into 3 things. You can see that it's analyzing all of the possible types. And let's see if it hopefully works when I do this. And if it only returned 2, which means one of those things is going to be nil. 2 good things. One thing is that it'll see that it's nil, and if you accidentally try to call something on it, then it'll notice the exception, which, as I said, it won't tell you about. And it'll also let you know that that left-hand side is never assigned defaults to nil. Very cool. Yes?
What's your comment about the double quotes? This is Perl.
What? I mean,
It takes more interpolation.
I mean, it's pretty.
Yeah, it doesn't. I benchmarked it one time. I still use 6 quotes.
It's extremely minimal, but I like it. So, no. But the good thing is that there's already. I'm sorry. There you go. I like that. No, but most importantly is that Laser does allow both tool-wide settings for which things you do want to be warned about, and it also allows. It doesn't have file-wide settings yet, but it does have line settings. You can add a comment to a line and say ignore. In this case, let's see. It didn't print the string that you actually specify, but I'm probably over time anyway. Because, as I said, it doesn't tell you. Remember the scumbag Steve thing? Yeah, that's part of how it needs to be better at. The other thing is that, I mean, because the type analysis is conservative, it's going to pick up on things that aren't even in the code, and that's part of an example where it may actually have picked up a type that never will happen. So, I mean, it doesn't even tell you about guaranteed exceptions it finds yet. The possible exceptions, that's going to be more interesting to figure out where that goes. But yeah. All right, so I think that's pretty much it. Any questions? Yes?
I think the SSA with Cartesian products may have been done in a paper in the book, Implementation of Advanced Programming, which came out around 91.
Okay, cool.
And basically what they did is they did that based off of scheme, and they had a corpus of primitives.
Nice.
They knew what the return types would be based off of the arguments.
Cool.
And I'm pretty sure they used SSA based on that.
Scheme's had a lot of great work on it. One of the most fascinating projects is a project called Stalin, which is called that because it brutally optimizes. And it has very slow compilation times, but it generates incredibly fast scheme. But anyway, yeah, next, anyone? I thought I saw a couple other hands. Yes? Reek? Oh, yeah. I mean, part of the reason I got interested in this because I was interested in code quality tools. And yeah, there's things like Reek, there's Rudy, there's all those different tools for that sort of thing. I think that, I mean, for things like finding code smells and stuff like that, I think that Laser could be a big benefit to that. A big part of what it does. I mean, this finds, if you do assignment in an if, it'll let you know about that. I think there's a lot of, what's the business word? Synergy. There we go. A lot of synergy for a lot of projects out there with what I've been doing. So, anyone else? All right. Cool. Thank you.